All right. Okay, so I, as usual, messed up a little bit, so I'm way behind schedule, and I have to do two things in one lecture, because I have to discuss unitarity and the conditions that follow from it. Well, I'd like to do two things today. I still promise you this discussion of unitarity and what it implies, in particular that scaling dimensions are real, dilatation operators are mission. I don't think I'll quite get there, but we'll do a very quick recap or a quick overview of unitarity conditions. And then the second thing I'd like to do is to discuss the conformal bootstrap, the numerical conformal bootstrap. And for that, we'll do a few computations in Mathematica with the conformal blocks. The reason I thought Mathematica is useful was because these conformal blocks are nasty functions, and it's not so hard to get an intuition from them, or to compute their value at certain values of the positions without some kind of computational tool, and Mathematica works pretty well for that. So that'll be the second bit of the lecture. Were there any questions about the previous lecture? Last lecture I started with lots of questions. We had a Q&A session. But is there anything left that you'd like to ask me now? Nothing now? Okay, great. Like I said, there's a discussion of unitarity that we need to have, but I'll cut it short. And so there is a better way to discuss unitarity, which involves the radial quantization picture, and there's a proper Hilbert space there, and this Hilbert space must have a positive definite inner product. From that you get nicely all the unitarity bounds, but there are shortcuts to these unitarity bounds, and I'll use the shortcuts at the moment. If you want the proper discussion, so the Hamiltonian discussion if you want, let's not say Hamiltonian, let's just say Hilbert space discussion. Then you can, for example, look at the lecture notes by David Simmons-Duffin. Tazi notes. This is just one example. There are a few other sources that you can ask about. You can ask me about later. What is the condition that I'll use in place of unitarity? So remember, unitarity is fundamentally something that you see in Lorentzian signature. The unitary in unitarity is e to the iht. It's the unitarity of the time evolution operator. That should be a unitary operator in your Hilbert space. In Euclidean signature, which is where I've been living in these lectures, unitarity signature. Unitarity translates to something called reflection positivity. And there is a rather famous and well-known correspondence between these two things, that if you have a theory in Euclidean signature that's reflection positive, then you can analytically continue to something that is unitary in Lorentzian signature, and vice versa. Lorentzian signature here. So often people slightly abuse language and they say the theory is unitary also in Euclidean signature, but then you have to be a bit more careful what you mean with unitarity. The proper thing to look at in Euclidean signature is called reflection positivity. And the map between the two is known as Osterwalder-Schroeder reconstruction theorem. What is reflection positivity? It's very nicely illustrated in a picture. It means that if you have some object, say a bunch of local operators, and it has maybe some tensor indices that point in a certain direction, like so, then if you reflect this, in, say, the Euclidean time direction, like so, and you compute the expectation value of this thing together with the reflected thing, then this is positive. Maybe you need to do some complex conjugation, so let me also add a little star. Like if there are complex fields in your theory, then you need to take the complex conjugation. If there's a spinor, you need to take the complex conjugate spinor. But then you get something. If you do that properly, you get something positive. And you also notice that you also need to reflect the space-time indices, like I indicated. And this is something that we can use. So well, what should I write? So assume I have an operator where this star operation is trivial. So like a real scalar field or a combination, a composite operator made from real scalar fields or real Hermitian observables. So let's say there are Hermitian. Then what does reflection positivity buy us? It buys us several things, and I'll just list them and give you quick proofs of them, because we have to go discuss other things. Let's consider a two-point function of local scalar operators like so. So I have one operator here at some minus t, one operator there at plus t. Then what is this thing? Well, we have already derived that this looks like 2 delta I, looks like this. So we know the functional form of this thing with some coefficient Cij. And now we see that the Cij is basically constrained to be positive on the diagonal. Cii is diagonal. But more generally, Cij must be a positive definite matrix that I'll write like this. Sorry? Like a tensor index. We'll get to an example in a second. So Cij is positive, and therefore it is a positive definite symmetric matrix, so I can diagonalize Cij. It's not some annoying matrix that I cannot diagonalize and set. And in fact, I can just choose Cij equals delta. It's not some matrix that is complex that I cannot diagonalize. If the operators are Hermitian, this is a nice matrix that is positive definite that I can diagonalize. So that's why in previous lectures and also in what follows, I can just take Cij to equal delta ij. So the matrix of two-point function, I just take it to be the identity matrix. So just that justifies that assumption. Oops.
This is on the plane. So
I'm sorry?
this is on the plane. So like a sphere or other like a manifold, complicated manifold, like a higher genus.
This is a matrix of two-point function. I don't know what the two-point function looks like on another manifold. This is the flat space two-point function. And the flat space two-point function was determined, the position dependence was determined, and there were some arbitrary coefficients. All I showed now is something about these coefficients. The curved space two-point function on a non-trivial manifold can be very complicated, and is not something I have said anything about.
I have a question. So what happens if there is some degeneracy?
Yeah, that's if there is degeneracy and it's not infinite. I've swept that under the rug. There's a finite degeneracy. This is a matrix, and the matrix must be positive definite, right? Because I can take arbitrary linear combinations, and I must get something positive by reflection positivity. That's the statement that the matrix is positive definite.
Yeah, but in the case of, for example, two-dimensional Rees conform field theory, there should be some different fields which have same dimension, and I don't think that can be diagonalized.
Well, let's just assume discrete spectrum. So, and finitely many operators per delta. That's an assumption I referred to very briefly in a previous lecture. Yeah, I'd like a finite temperature. I'd like the function, the partition function at finite temperature to make sense, for example, something that traces over the Hilbert space and shows you that there's finitely many operators per delta. Another thing is, for example, another nice object I can compute is the first descendant of this primary operator, like so. And let me put the descendant, the derivative that I take by computing to get the descendant, let me put it in the t direction. So now I need to add an extra minus sign here because I want it reflected, the tensor index. So I add a minus sign to get the reflection. And then this is also positive. Let's take identical operators for now. And this is also positive from by reflection positivity. But I can also compute what this is. And if you work out the derivatives, then you get something like, well, this is 1 now in new conventions, 2 delta plus 2. And so what you get from this is that if this is positive, then we see that delta is also positive. So reflection positivity again tells me that the deltas have to be positive. They can't be arbitrary, complicated, complex, or negative numbers. We already knew that from cluster decomposition, but it's nice to see it confirmed here. Actually, there's another option, namely delta equals 0. But if delta equals 0, then this two-point function is 0. And in a unitary theory, that means that the actual operator is 0. So dt OI is 0. And if that is the case, if the operator does not depend on the position, then the only thing it can be, you can show, is the identity operator. So there's one operator with dimension 0, which is the identity operator. And then dt OI is 0. And delta must also be 0. But for operators that are not the identity operator, delta is positive. And I need a few more details that I'll just state, a few more conditions that I'll just state. So if you do this, you take the Laplacian, like so, of a scalar operator, then this is also positive by reflection positivity. And this implies that delta, you get something similar, right? You get some deltas coming down from taking the derivatives. And you will find that delta is greater than or equal to d minus 2 over 2 for scalar operators. For scalar operators that are not the identity, of course. Because if delta is less than that, there's a minus sign that you get. And that's in contradiction with reflection positivity.
So this inequality also can be satisfied if both the two prefactors are negative, which can give you some possible values of delta that are negative?
Sorry, it can
inequality, the inequality that you've written where you have both the prefactors, right? 2 delta and 2 delta plus 1, both of them individually being negative, which can give you possibly some delta which are negative.
Oh, you mean if delta is sufficiently negative?
Yeah.
Yeah, that is true here. But then you have to go down and down and down.
Okay, so higher and higher.
And at some point you rule that out.
Okay.
Yeah, thanks. Yeah. So eventually you'll see that this has to be true. So this is a simple exercise. You can take the Laplacian of this two-point function and then evaluate it at the corresponding points, and you'll find this. Finally, I need to also show that for delta, I mean, again, by taking a derivative of a two-point function like so and demanding that it obeys reflection positivity, you'll show something like this. And this is, I'll just write it down because we need it later. Symmetric, traceless tensors x u1 to mu now. So if you have a tensor that is symmetric in all its indices, it's completely traceless, you can solve the word identity, you can find the two-point function, you can write it down like so, you take one derivative like so, and then you'll find that if you orient the indices in the right way, corresponding, so that you have something that should be positive by reflection positivity, you'll find this bound. It's also a bound on the scaling dimension for symmetric traceless tensors. Works exactly the same way. I'm not, that's the second time. I'm not going to revisit it now because I really don't have time. Or review it now because I don't have time for that. And finally, what you can also show is that the lambda 1, 2, 3 are real numbers. And they're not complex. That's also important. Finally, I should state one more fact. That is that in the operator product expansion of two operators, this identity operator, or two identical operators, OI, OI, the identity operator must appear. So it's this plus other operators. And this is basically, well, it's a consequence again of reflection positivity. It means that if you have an operator product expansion, then you can apply it to the two-point function. And if you apply it to the two-point function, you can get a sum of one-point functions. But as it happens, all the one-point functions of all the other operators are 0. And so what you see in the two-point function is really the contribution of the identity operator, the operator product expansion. And in principle, there should be an arbitrary C acting on this. But remember, this C is a very complicated differential operator. The derivatives of the identity go away. And so this thing is not there for the identity operator. It's really just this factor. And this factor, of course, precisely corresponds to the two-point function, basically because the expectation value of the identity operator is 1. So if you take the expectation value of both sides, you get here the two-point function, here you get the known answer, and the expectation value of other operators disappears. So that's a little comment about the operator product expansion for two identical operators. The identity operator must appear. Yeah, sorry, why this? Thanks. Yeah?
What about other representation?
The identity must always appear in the OP of two identical operators, but I won't be needing it except for scaling. Oh, you're asking, oh, that's a good, fun question. Yeah, what's the unitarity bound for other representations? What about antisymmetric tensors? I don't know, but it's known. It's easily found by considering the two-point function of derivatives or by looking at the Hamiltonian picture that I told you I was skipping. But you can find it, and it's probably somewhere in the literature out there. So, in fact, yeah, you have antisymmetric tensors. Of course, in 6 dimensions, you have you have multiple Lorentz. Well, even as Thomas said, in 2 dimensions, you have 2 labels. So you can also ask about spinors in any representation of SOD. In 6, you have 3 labels. So it's just a matter of representation. Okay, these are facts. And I'm sorry that I don't have the time to prove them in more detail.
Sorry, I have a question. What about the unitary bound for higher descendant operator?
So what I want to say is that this is for primaries, but as it happens, then it's also true for descendant. But for scalar, so this is primary, and this is primary. Trace this primary. Thanks. But so for descendants, if I know the norm of the dimension of the primary, then I know the dimension of the descendant, because it is +1, +2, +3, +4, +5, so on, right? If I take 1, 2, 3, 4, 5 derivatives. So there's no separate bound for descendants, because descendants don't have an independent scaling dimension.
Yes, but for this, you only take a 2 derivative of the primary.
Yeah.
If you take higher derivative of primary, does it give another new constraints?
Oh,
for the scaling
no,
dimension?
they will not. As it happens, they will not give you new constraints. So this is the strongest bound. And then you can prove, again, using things that I did not explain, that the representation, all the further descendants also have positive norm in this sense.
Thanks.
So these are the best possible bounds. And you can actually show that these are, when they're saturated, what happens if delta is equal to d minus 2 over 2? Well, then this thing actually becomes 0. And if the Laplacian of an operator is 0, then we recognize this to be a free massless scalar field. Because that satisfies the Klein-Gordon equation. In the massless case, Laplacian of phi is 0. So when the bound is saturated, you have a free massless scalar here. And similarly, when the bound is saturated here, you have a conserved current. For example, let's take L equals 2. Then we see that delta is greater than or equal to D. And when delta is equal to D, that's the stress tensor, then the first descendant is 0, or there's a 0 norm descendant, which is the divergence of the stress tensor, which is 0. So these bounds, these numbers, when they're saturated, there's some null state, as people say it. There's some descendant that becomes 0. Okay, that's all I need, and therefore all I wanted to say about unitarity, unless there are more questions. No? Good. Keep this in mind. Let's go back now to conformal blocks. Let's go back to crossing. So we will look at a 4-point function of identical primary scalar operators that I'm going to call sigma. We have derived that this 4-point function has a decomposition as a sum into conformal blocks, where a sum over primaries k with 3-point function squared, so lambda sigma sigma k squared, and then a conformal block, and let me write it in a slightly different way from what I did yesterday. x12 to the 2 delta sigma, x34 to the 2 delta sigma, g delta k, lk, z bar, like so, like this. So this thing in parentheses is, of course, I'm now trying to maximally confuse you, because this is the thing I called g delta L of x1 to x4 from yesterday. And now I have factored out the x12 and the x34 and written this as a function of z and z bar, which you may remember we're given like z bar is the u cross ratio. It's x12 squared, x34 squared, x13 squared, x24 squared, and 1 minus z bar. It's the v cross ratio, which is 1, 2, 3, 1, 4, 1, 4 squared, 2, 3 squared, 1, 3 squared, 2, 4 squared. So what you see here is that something that I also wrote down basically when we solved the word identities for 4-point function. So what's implicit here is that actually every conformal block solves the word identities implicitly, directly, or solves the word identities automatically. So conformal blocks always look like this. That's just the fact of life. The conformal blocks were known functions, and I now claim they always look like this. This is just what conformal blocks look like. If you don't believe me, I've given you the formula to compute conformal blocks, so you can check this yourself. And then, of course, this is equal to the same thing with, well, there's the other cross channel, but that's just the same as swapping up two operators. For example, I can swap 1 and 3. And let me combine the two, or, well, I guess I can just write it down. So this is the same sum over primaries, k lambda sigma sigma k squared 1 over x. I'm going to swap 1 and 3 here. Delta sigma x2 3 to delta sigma g and delta k lk. And now what happens to the argument z and z bar if I swap 1 and 3? Well, let's see. If I swap 1 and 3 here, the denominators are unchanged, and the numerators, they swap. So you get z goes to 1 minus z, and z bar goes to 1 minus z bar. So 1 minus z, 1 minus z bar, like so. Right, this was the crossing symmetry equation that we derived in the previous thing, and let's now recall, or I want to get to a few formulas on the board that look nice. So, okay, let's first recall the set of operators that we have here, the sum of operators. So these are all primaries operators. There's first of all the identity, which contributes because it's identical operator, so the identity must appear. Then there are scalars. These have spin 0. L here is the spin of the operator with delta greater than d minus 2 over 2. And then we have symmetric traceless tensors with delta greater than or equal to L plus d minus 2. So as it happens in the OPE of a scalar with itself, the only tensors that can appear are symmetric traceless tensors. They obey this unitarity bound. And furthermore, because the operator is even, L must be an even number. So spin 1, 3, 5 cannot appear. L is only an even number. This is a simple fact of Bose's symmetry, and you can easily find this yourself by trying to write a 3-point structure with 2 identical scalars and one, say, dimension 3 or spin 3 guy, traceless symmetric tensor. And you'll try to solve the word identities, make it symmetric under exchange of 1 and 2, and you'll find there's no tensor structure that does the job. So, one thing that we know is that the identity must always appear. So I'll factor out the conformal block that corresponds to the identity operator, and then we have all the non-trivial operators themselves separately in some big sum. Furthermore, I'll rewrite the thing a little bit to say that 0 is equal to sum over all primaries. So I'll combine these two terms, sum of all primaries k, not the identity, which is lambda phi phi k squared. I'll manipulate this equation later on, so I'll leave some space here and there. Some functions, so which depends on delta L z bar plus f1 delta phi ZZ bar. So what are these Fs? Well, they're just this block minus that block, and I can sort of combine, I can multiply the whole thing with x1 4 squared, x2 3 squared to get some nicer structure just in terms of the cross ratios, Z and Z bar. So I have to tell you what Z and Z bar, what the Fs are. So F delta phi delta L Z Z bar is 1 minus Z, 1 minus Z bar to the delta phi, or delta sigma, sorry, delta sigma. Sigma delta sigma. Times G delta L Z Z bar minus the thing swapped Z Z bar swapped with 1 minus Z, 1 minus Z bar. And this F for the identity operator, it just depends on delta sigma, Z and Z bar. As it happens in these conventions, for the identity conformal block, this G is just 1. And so it's very easy to see that this is just a prefactor, 1 minus Z, 1 minus Z bar, delta sigma, minus this thing being swapped. Okay, I hope you're all with me. What happened here also is that these prefactors, x1 2 squared, x3 4 squared, and so on, got combined into something that is v or u, and that's where I get the 1 minus z and 1 minus z bar for raised to the power delta sigma. So I've been super explicit. I hope you're all with me and you believe these equations. And if not, please ask it now because I'm going to type them up and do some numerics with them. These are okay? These are the crossing equations. So this, with those f's, these are the crossing, this is a form of the crossing equations that we are now going to play numerical games with.
So this is any dimension? Or?
This is still in any dimension. Yeah, the conformal blocks, they depend on the space-time dimension D. That's where it's hidden.
How about 1D?
D equals 1? Yeah, would work. There's only one cross ratio there, so z bar is equal to z, but technically that's the only and there are no scalars, and your representation is a bit sick, but you have your little group is Z2, right? So you have factors and scalars. So okay, let's do a little bit of numerical experimentation with this crossing symmetry equation and see if we can derive something about the spectrum of conformal field theories just from these equations. Oh, I guess you can definitely read it now. Somehow the resolution has changed. Let me magnify it a little bit less. Okay, so we have to type up these conformal blocks. So remember what a block was. There was sort of a thing like a half block, which depends on h, z. So I'm using Mathematica here, by the way, which is nice because it has a hypergeometric function built in. So h, to h, z. So what I'm doing here is we're going to specialize to d equals 2. So let's make it a bit smaller. So oops. From now on, d equals 2, unitary CFT. So I have this half block, and then the full block as a function of delta j. This is an equation I wrote in the previous lecture, is just the half block, oops. Well, I can do this, half block of delta plus j over 2 z bar times the same thing. Oh, it does not depend on z bar. Sorry. Like so, z bar minus this. And now we're basically there because I have to symmetrize this in z bar and z. So these are the two-dimensional conformal blocks, and these are the things I can play with. Now, I don't quite have conformal blocks in these equations. I have these funny functions f. So let's implement those as well. So let's say what is f? It depends. What does f depend on? On delta sigma, delta L, delta J, z and z bar. So we do a delta sigma, delta J, z and z bar. So I have to do this because Mathematica makes me do it. And then I have 1 minus z, 1 minus z bar, raised to the power delta sigma. Well, let me call it delta s, it's easier to type. Then the block, delta j z z bar, like so. And then I have to symmetrize. So we'll do this minus the thing where z goes to 1 minus z, like so. 1 minus, oops, 1 minus. And we have an f for the identity, so that is easily added. F id for identity, it does not depend on delta and j, and it's just a thing with the block set to 1. Like so. Good. That was a bit of typing. Sorry, it was a little slow. So now we can see how this equation is obeyed. And one interesting, or one sort of natural starting point maybe, to pick some values of z and z bar. Because notice, this equation must be true for all values of z and z bar, right? The 0 here does not depend on z and z bar, but this here does. And so let's just pick some values and see how this equation is obeyed. So let's pick, if I do, like I said in response to questions, you can actually consider complex x's, and similarly you can consider complex u's and v's, and you can actually, well, okay, it's a little bit of a long story about which values of u and v you have to pick, because for some values of u, v, and so for some values of z and z bar, this thing may not converge, but I'll pick z and z bar to lie between 0 and 1, both. And there you can show they're real independent coordinates despite the notation. So we can, and you can show that in this little square defined by z bar in the unit interval, there's no problem with convergence. So we can consider, for example, f. We also have to pick a delta sigma. So let's add the assumption that delta sigma equals 1/8. That is just a nice value in 2 dimensions. It's above the unitarity bound, so it's a perfectly valid value to consider. So delta s, then we have, well, we want to see what the blocks do, say as a function of delta for different values of j, for z equals 1/2, and z bar, say, 1/4, something like this. So I'd like to plot this from where delta goes to from the unitarity bound, which is j and v equals to say j plus 20, and maybe we want to make a little table where j ranges from 0 to 10 in steps of 2. Oh. So plot this. Maybe we should add a bit which label j equals string j. So let's add a bit of a label so that I know which j is which. Okay, the axes are different, so let's do this. Axis origin to 0, 0. Okay, so now we have a bunch of plots. So what is happening here? We have some operators in our spectrum, some k's here, and we have the f evaluated for different values of j at some particular value of z and z bar. And what we have to get, we have to pick a bunch of deltas and j's, multiply them with lambda squared, and sum the whole thing, and then we have to get 0. Now, how are we going to get 0? Notice these lambdas are real, and their square is positive. So we have to take a positive linear combinations of these f's with certain values of delta. Now, interestingly, for almost all values of j that I picked and delta, these things are negative. And as it happens, I haven't shown you the extent, like all j's and all deltas, but we can scroll down a bit. I did a few more j's. And you see they're all, almost everywhere, they're negative. This in fact happens, it continues all the way to infinite delta. These things are negative. So for this value of z and z bar, here you just get a bunch of negative things. They're not negative everywhere. For j equals 0, very close to 0, they're positive. And of course, there's the identity. So let's see what the identity is. F, so the identity, that was this one, right? Yeah, I don't know what that is. Ah, that's positive. So that's where the positive number comes from. Maybe with some j equals 0. Maybe there's some contribution from a scalar with a very low scaling dimension. But all the spin 2 guys, spin 4 guys, and the scalars with a large dimension, they all contribute negatively. The reason I can get 0 in any conformal field theory is because this is positive. And maybe a low-lying scalar gives a positive contribution. But this already illustrates there's some tension here, right? It's not at all obvious that you can always that you can always obey crossing symmetry. For example, if you suppose there's no such scalar with a dimension less than 1 in the OPE of sigma, so we'll say let sigma, assume sigma times sigma goes to, so this is a schematic way to denote the OPE, goes to 1 plus epsilon, which is a scalar, plus other stuff, which is scalars with delta greater than delta epsilon and tensors. So suppose the OPE of sigma with itself looks like this. And suppose that the first scalar is called epsilon and that its dimension is somewhere like 5 and all the rest is higher than 5. Then you see that all the junk here, all the stuff here contributes negatively, and this contributes positively. But that, for example, also means that your positive contribution is bounded at 0.11 or something, whatever it was, 0.11. And so if you have a coefficient here that's gigantic, you get a negative contribution that's gigantic, and you will never be able to compensate it because everything else is also negative. So already there's tension. This is where the tension comes from, that you cannot have arbitrarily large negative OPE coefficients, for example. That just doesn't work. And in this way, we can get non-trivial bounds on, say, OPE coefficients in a conformal field theory by just exploring the crossing symmetry equations a little bit, like so. Now, one thing you can do is just sample at different points and look around in the space of all positions, all z and z bar, for which this thing converges, and just try to see what z and z bar gives you the best bound. But then you just sample one bound at a time. And of course, you can be more clever, because this is a linear equation for these f's. And so I can say, well, zi, 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 zi. What did I say? you can pick Zi, a bunch of points. I runs from 1 to, well, whatever your numerical capacity allows you to do. So some n. You cannot check for every point, but you can check for a finite number of points. And what you can then do is see that this equation has to be true for any value of Zi's. So for each I, you have a separate equation. But I can take a linear combination of these equations with arbitrary coefficients, like so, sum over I, with some coefficients alpha I. And then it's still true. On the left-hand side, I have a linear combination of zeros. Well, that's 0. On the right-hand side, I have this linear combination. But now by linearity, of course, I can swap these sums. So I can do something like this. This is why I left some space here. I equals 1 to n, alpha I, like this. And here also, sum I equals 1 and alpha I. And now my game can be to pick suitable values of Z. If you're given the Zi's, you're searching for some suitable alpha i's that gives you the best constraints. So you have a finite dimensional space of alpha i's in which you're searching to get whatever constraints you want to find. So for example, I can take a linear combination. I think there's a nice one that I searched for and I found at some point. It's f minus 1/2 this one, 1/2 1/8. Let me cheat because I did some of this already. Minus, yes, okay. You didn't see that, right? This is just spontaneous. I'm just inventing this. I didn't prepare this at all. So voila, this is it's a linear combination. I did pick 2 points. Which points? 1/2 1/4 and 1/2 1/8. I took a linear combination with the coefficient 1 and minus 1/2. And we get plots that look like this. Oh, and we should also check the identity. So let's check the identity. Minus 1/2 times this. 1/2 1/8. Now I have something that's still positive on the identity. So the identity contributes positively. Barely, but it contributes positively. 0.01. And what do all the spins do? Well, spin 10, spin 8, spin 6, spin 4, spin 2, and spin 0 for large enough dimension all contribute positively also. So almost everything here is positive. The lambda squares are positive. But I have to get 0. So how do I get 0? Well, here. So it turns out this is not negative. If you zoom in, here it's positive still. This is all positive. If you go to larger deltas or larger j's, it's all positive. But the only place where this thing is negative is right there. And so I have derived for you a non-trivial theorem that, well, it crosses at about 4, but let's say it's 5 to be safe, that in any unitary two-dimensional conformal field theory, if there is a scalar of dimension 1/8, then I can look at its 4-point function. And if the OPE is of this form, then this delta epsilon has to be less than 4 point something. Right? And it's completely rigorous. And it's a resulting quantum field theory for which I did not need to compute Feynman diagrams. I did not need to do a lattice simulation. It just follows from the general principles of conformal invariance, and the OPE, and all the stuff we discussed. And we get to these kind of non-trivial numerical results. Question?
So you sum up some finite number of spins. But,
yes.
What if some large, some other spins, some suddenly maybe
yeah, sure.
negatively appear?
If I do larger spins, then my code gets slower.
So there's some kind of approximation that you don't have to, kind of truncation is more reasonable.
You see, it's like I promised, it's so positive. Yes, of course. So at some point maybe, and also for very large delta, right? Because what if these things change sign somewhere for large delta? So of course you have to be careful here. And you have to check, you can do some approximations for large spin or large delta or both and see that it's positive. You can match your asymptotic analysis to the numerical plots like so. You can be very careful and show this rigorously. Yeah, that's not what I've done here.
So is there any reason in the plots, the higher spin structures, I mean the graph for the higher spin ones are not really reaching the y-axis?
No, the fact that they're not zero, I just picked a linear combination. So I picked a linear combination such that they're all positive. If you change the coefficient, I had a relative coefficient of -1/2. This goes up and down, it changes a little bit.
No, I'm saying, is there...
Oh, the y-axis, sorry.
Yeah.
I got my axis confused. Delta is for a spin. Did I not write it? There. Delta is greater than L. So my spin 2 operators in a unitary theory, I only have to check in 2 dimensions, starting at 2.
Right.
And the spin 4 operators I have to check starting at 4 and 6 and 8
Okay.
and so on. So that's why I don't have to check lower D, because that would lower delta, that would violate unitarity from something I wrote half an hour ago.
Right. Okay, thank you.
Our question?
Mm-hmm.
I think that, I'm not sure, you told that delta was fixed to be 1/8.
Yeah.
So Ising belongs to there, right? No?
Yes, absolutely.
Yes, I just got confused about the numerics. So 1/8 is Ising, right?
1/8 is Ising, yes.
Ising. So Ising must be there.
Ising is there, yes. That's why I picked 1/8. Because, but it works, no? Ising, what is epsilon in Ising?
Energy?
Yeah, but what's the dimension?
1/2? 1/2, right?
Well, it's definitely less than 5, right? Because I've just shown you rigorously that it must be less than 5. It's actually 1. We're not working with the chiral dimensions. So you have, so sigma is twice 1/16, and epsilon is twice 1/2. If you know about the 2D Ising. So sigma is 1/8 and epsilon is 1.
Yeah.
So I now have a theorem that I've proven modulo the numerical subtleties that I discussed. Consider a 2D, no space, 2D unitary CFT. If you want to be precise, it has to have discrete spectrum. There has to be some other subtleties that I don't want, that I'll just shove into my definition of what I mean with the CFT. So it's my type of CFT, such that the conformal block decomposition works. With a primary scalar sigma with delta sigma equals 1/8, and OPE sigma times sigma equals 1 plus epsilon and so on. Okay, this was a mess. I hope you're still with me. If you have all of this, then delta epsilon must be less than or equal to some number that I'll conservatively take to be 5. It's really like 4 point something, that's what we've shown, but it's definitely less than 5. Right? This is now a theorem about 2D unitary CFTs. We've just derived it on the spot. Any questions? Okay, but how did we derive this theorem? We derived it by picking 2 values of z and z bar, 1/2, 1/4, 1/2, 1/8. We picked alphas, and in this 2-dimensional alpha space, before I prepared the lecture, before I gave this lecture, I searched a little bit and I found some bounds. But what about other values of alpha here? 1 minus 1/2 are the 2 values I picked. So what about others? Can you get better bounds? Can you pick more values of z, and then you have a higher dimensional space to search in, and so on and so on. So you can ask lots of questions, and in particular, you can ask whether this delta epsilon, this bound on the first scalar in the OPE of sigma with itself, can be brought down. And so the answer is yes, you can work harder. Well, not you. The computer can work harder. The fun part of this numerical game is that the computer does all the work. And you can fix a bunch of z's. You can then search in this space of all the possible alphas. And this goes under the name of, this is actually a thing called convex optimization. That's a kind of algorithm that you have to solve. You have to find the alphas such that all the plots come out positive everywhere above your upper bound, and it's also positive on the identity, so it's searching with constraint. And there's a convex, it turns out to be a complex thing, and so you have a complex optimization problem to solve. This will give you that delta epsilon is less than or equal to a little bit harder, 1.01. Say. If you work really hard, you can add another 0, 1.001, and so on. And this is, of course, now, like we see that our bound comes down and down and down. At some point, it seems to stop, and it stops at the value very close to 1. And there exists, as several of you probably know, there exists a two-dimensional conformal field theory for which the scaling dimensions are known. There exists an operator, scalar operator sigma, with a scaling dimension of 1/8, with an OPE exactly like I said. In particular, interestingly, sigma does not appear in its own OPE because 2D Ising has a Z2 symmetry. So there's really, the first scalar that appears in the OPE is not sigma itself, and delta epsilon equals 1. So what the bootstrap, what we found now with the bootstrap is that, with this numerical method, is that you can get very close to this delta epsilon. And there's no solution to this 2D Ising model. And there's no, for example, there's no deformation of the 2D Ising model where you would make delta epsilon a little bit bigger, because the moment you go above 1.01, you will never ever be able to obey the crossing equation. Of course, in 2D Ising, we know these things because two-dimensional CFTs have an extra symmetry called Virasoro symmetry, and so we know these things exactly. But the game I just played is something I can also play in 3 dimensions. And in 3 dimensions, we don't have Virasoro symmetry, but we do have this method. And so we are able to get results also in 3-dimensional CFTs.
The configuration you consider here is in Euclidean region?
It's on the interface of, it's Lorentzian actually, but the points are still space-like separated.
So Z and Z bar is independent, or?
Yeah, they're real and independent. I took them to be 1/2 1/4, 1/8, 1/2 1/8. As it turns out, this is a Lorentzian separation, but all the xij squared are still positive. So, okay, it's a bit subtle because xij squared are all positive, so the separations are all space-like. But the Euclidean space, you cannot find 4 points such that z is 1/4 and z bar equals 1/8. You'd have to go to Lorentzian signature.
Yes, okay. Thank you.
I didn't want to discuss that too much. You can ask me afterwards precisely about what is Lorentzian and what's Euclidean.
That's a one short question. So did you play the same game with delta sigma replaced by 1/2 instead of 1/8?
I said it 1/8. Yeah, you can do 1/2. Then you get a bound. Do you want me to do it? I'm not sure this still gives me a good bound.
Yes. So I have some reason. No.
Oh, it's maybe this coefficient is very bad for delta sigma equals 1/2. Oh, this looks negative. Okay, we'll see. And what about this? This is still positive. Now we have to worry about this guy, right? Okay. I think we're out of luck with my coefficient of -1/2. Maybe we have to search a little bit. I can try to find a different coefficient, but I'm not going to do it now because I think it's going to be super boring.
So what is the evaluation of structure constant in this case?
The structure where was the question?
Yeah, lambda.
What was your question then?
Yeah, so in Yijing, you can also evaluate the structure of lambda.
Yeah, but I have not done so, right? My result is agnostic about the structure constant. Because all I need is that
I
this
see.
square
So
is
you
positive.
cannot evaluate that.
I could vary them, like at the beginning I told you that there was a structure constant cannot be huge, for example, for a spin. So I could also play similar games where I get bounds on the structure constants. But yeah, please ask me afterwards. It's a bit of a orthogonal direction to where I want to go. But yeah, this bound is independent of the structure constant. There was no assumption there. So okay, this is basically what I wanted to show numerically. Now I'd like to just flash a few results. Let's say you have a computer and you have implemented this complex optimization procedure, and you've gotten this delta epsilon to be equal to, so if I plot here delta sigma as a function, or delta epsilon is a function of delta epsilon, the bound on delta epsilon is a function of delta sigma. For 1/8, we have 1.01, and everything here is excluded. No way that delta epsilon can be there. And everything below that, well, what about below that? It's not quite allowed, right? Because we've only checked the crossing equation at a few points. And there may be other crossing equations. For example, there's the 4-point function of epsilon, and there's correlation functions of epsilon and sigma mixed. So it's not always true that you can obey crossing here. Here we definitely cannot, because I found already one crossing equation which cannot be obeyed. Here, all we can say is maybe. So it's not a yes, it's a maybe. And then of course you can play the same game for different values of delta sigma. So you get, again, some excluded region, some allowed region. And in fact, what you get is a plot that looks a bit like this. So this is all no, and this is all maybe. And this is what the plot looks like. If you repeat this experiment with multiple points, this is the kind of plot, very qualitatively speaking, that you get for two-dimensional conformal field theories, where you assume this structure of the OPU of sigma. And you can plot what are known. 2 dimensions is great because we have Virasor, so we have 1 million solutions to crossing equations. 2D Ising sits precisely here, just below the bound. There are other minimal models that sit here, close to the bound. There's solutions to crossing that you can get here. There's actually a line of solutions to crossing. There's some other minimal models. I don't know. Some other correlation functions that just all sit in the allowed region. They better sit in the allowed region, otherwise something would have been horribly wrong. Do the CFTs. But like I said, you can do the same in any dimension. So let's do 3D CFTs. This is from sigma, 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 sigma. But I can also analyze the crossing equations. That's a little bit more involved from multiple correlation functions. Like so. I cannot, but some people can. So this is for what I'm now about to show is the result work by David Simmons-Duffin, David Poland, Philip Haas, and building on a lot of papers by other people. So if you take these 3 correlation functions, you analyze the crossing equations, like I said, and no further scalars with delta less than 3. So there are no further relevant scalars. They don't, which is a natural assumption that you can make. I don't want to go into this, but this is to do with the renormalization group flow. So if you make this assumption, you analyze these correlation functions, then you get something that looks like this as a function of delta sigma, delta epsilon. So you get some junk here, which I'm not particularly interested in. And you get a very, very small island here of values of delta sigma and delta epsilon for which the crossing symmetries are okay. I'm shading the other way around. So here it's no, and here it's maybe. And this very small island is also maybe. And this very small island happens to be very close to known values. The delta sigma and delta epsilon that you get here happen to be super close to the experimental or Monte Carlo, the results that people have found for the three-dimensional Ising model. And here there's no Virasoro symmetry, so these numbers are also not so nice. And what they have shown with their numerical work is that that delta sigma is now super precisely known to be between 0.51814999. It's a really small island, 0.518479. And similarly, delta epsilon is 1.412635 or 1.412615. So they have very precise determination of these two scaling dimensions, which they found by analyzing the crossing equations. And so remember that I drew in the very first lecture this picture where you have the specific heat, which diverges as a function of the temperature in some second order phase transition. The second order, the power with which the specific heat diverges is 2 minus 3 over 3 minus delta epsilon. And if I just plug in these numbers, I get that alpha, this power, is between these two numbers. I said it's approximately 0.11. These are the best, most precise determinations of alpha that we currently have. And so what I like about this is that this is just follows from consistency conditions, right? So where did we start? We started discussing CFTs. We had this enhancement of skill to conformal. Then we had some word identities. Then we had the Hamiltonian picture where you see in radial quantization that there's a state operator correspondence. From the state operator correspondence, we were able to find the conformal block decomposition and argue that it converged. There were a few things about unitarity, but all of that followed from basic general consistency conditions. And what comes out if you give this this crossing symmetry equations to the computer and you analyze them cleverly are very precise numerical values for scaling dimensions, which you can in principle directly relate to observable quantities. So this is the thing that people call the conformal bootstrap. The bootstrap is the idea of pulling yourself up by your own bootstrap, which normally you cannot do. But here it miraculously seems to work, that we have this idea that all we need is some general consistency conditions in the form of these crossing equations and a very powerful computer. And if we combine these two things and we do it in the right way, then what comes out are definite predictions for experimental, or definite predictions for observables, like so. Time is basically up. Are there questions? I have 10 minutes or so? 10 minutes, okay, I could even say a little bit more.
How much computing power do you need? Just a PC or supercomputer?
No, this is on a cluster. So it's not a supercomputer. Supercomputer is a big thing where all the cores talk to each other. The reason it's not necessary to have a supercomputer is that what you do is you just eliminate point by point. And so that's parallelizable. You can just give 1,000 computers 1,000 different points, and they each eliminate it, except maybe 2 or 3 computers come back and say, well, yes. And then you zoom in a little bit, you do a similar grid, and so on. So it's a big computer. It's definitely a few orders of magnitude less, I think, than what you needed to get the best Monte Carlo result. Any more questions? So you can, of course, ask, and this is nice, this is really cool, you have the 3-dimensional Ising model, and for some miraculous reason, people were able to determine these scaling dimensions very accurately from just 3 correlation functions. So you can ask, what else do the crossing equations know about? So here I made some assumption. And of course I can make other assumptions. I can, for example, assume that there's some flavor symmetry in the game. And then say an ON flavor symmetry. Then each of these get little indices. ON indices, you have crossing equations where you have to take into account sometimes you have to contract the indices in an appropriate manner. So everything gets dressed up a little bit with indices. But otherwise the problem is qualitatively the same, and you can get similar results for the ON models in 3 dimensions. But you can, of course, also do different things. So for example, one thing you can look at is superconformal theories that Thomas talked about also. And that'll give you something that we've come to call the superconformal bootstrap. And then everything just becomes super. So in some sense, these fields here now become superfields. You have things called superconformal blocks. You have multiple tensor structures, but if you basically just add fermionic directions to everything, you can compute superconformal blocks. That's not something that I've done, but Dolan and Osborne have worked a lot on computing superconformal blocks. And with these superconformal blocks, you can analyze the constraints of crossing symmetry for superconformal field theories. So what we did is, or what we and many other people did, is various amounts of supersymmetry in various dimensions. Thomas gave you a list of potential superconformal field theories, and for each of these, you can pick an appropriate operator and analyze the crossing symmetry equation. So there's a huge amount of work that you could in principle do. One particularly nice example, since I have a few minutes left, are the 60 2,0 theories, which are 6-dimensional, maximally supersymmetric conformal field theories. And they come, well, they're interesting because we don't really have a Lagrangian description. We know very little about them. They just come from string theory. And string theory tells us these theories presumably exist. In fact, they come in an ADE classification. And the A-type theories are also interesting because what they describe, they're supposedly the low energy. So A-type, they describe supposedly the low energy dynamics so AN is n plus 1 and 5 branes in flat space. So if you're interested in what these branes do in 11-dimensional flat space in M theory, then their low energy dynamics is described with these kind of theories. And so you can ask, well, do the crossing equations know about M theory? And can we extract that information from a superconformal bootstrap by looking at that, by giving these crossing equations to the computer? And we did that. And we don't quite have the rigorous theorem because we have some our numerics were a little bit slower, so let me just phrase it as a conjecture. But the conjecture is the following. In a unitary, non-free 60(2,0) superconformal field theory, it must be true that this a thing called the central charge, CT, is greater than or equal to approximately 2.98. And this is, so now I have to tell you what this CT is. For now, since I don't have too much time, let's just say that CT is related to an OPE coefficient in the 3-point function of the stress tensor. So there are, in fact, 3 possible 3-point function. One of them, if you normalize things appropriately, is basically the inverse of the central charge. So there's an OPE coefficient, and there was a question, can you bound OPE coefficient? Yes, you can. And if you bound OPE coefficient, you get upper bound on OPE coefficients, and therefore a lower bound on the central charge, which happens to come out to something like 24.98. Actually, this is conjectural because we did some extrapolations. The rigorous result is 21.45 or something, but if you let the computer work harder, we believe it's going to converge to a value like approximately this. And very nicely, if you take the A0 theory of one brane, it's a free theory, so that doesn't fall in its classification. If you then take the A1 theory, which is 2 M5 branes, then T for the A1 theory, and you can guess this, CT is known from other considerations to be equal to 25. So it is precisely numerically very, very close to the value that we just extracted from the crossing equations. So this gives some hope that these exotic 2,0 theories can actually be analyzed by just the crossing equation. So from the consistency condition, we have a match with something that other people already knew, but we can get other values for other observables like scaling dimensions and OPE coefficients that people did not know about before. And we can now get them very easily numerically. So in some sense, we can maybe try to define these theories because there's no other proper definition of them. If you don't know M theory, for which there certainly is no definition at the moment, maybe we can define these theories as the solution to the crossing equations at C equals 25.
Sorry, can I ask a question?
Yes.
Do we know the exact value of CT for AN theory? General
Yes.
N?
Yeah, we know it but you have to combine a few ingredients. Some analysis involving anomalies, the supergravity limit, and correction.
And it shows some N cubic behavior.
There's N cubed, yes, there's an N cubed, exactly. For very large N, as it happens, the central charge scales like N cubed. Yeah. And so, in fact, the central charge is a degree 3 polynomial in N. I don't have it quite, I don't know it off the top of my head. For N equals 1, I just know it's 25. For N equals 2, I think the next guy is 98 or something. Some number. Okay. Questions still? I think the chair is getting a little nervous. Okay, still good? Okay. I don't think so, but yes, it's a numerical game. So maybe there's like a microscopic island somewhere. I don't think so, because yeah, you have to, things get a little bit hairy. There are all kinds of subtleties, right? We are not going to be able to check infinite spins. We're not going to be able to check all deltas consecutively. So actually what we do is we approximate the blocks with polynomials in delta. So we have something, and then we can check that the polynomial is always positive. But it's still an approximation. So what if you refine your approximation? Maybe you find somewhere that it's negative. But that doesn't seem at all to be the case because you can just test a few points by including some extra spins and some extra deltas, and you see no change. Similarly, you can refine your grids even more and see there's no change. There's also a little bit of convexity here going on. So, in fact, if you test a bunch of deltas, there's some interpolation that also works. So we think it's pretty safe, but yeah, there's subtleties like that if you really work in this, you have to be careful about.
Can I ask another question? You used crossing symmetry as a constraint, but I've heard of something like modular bootstrap. And are there any kind of constraints that can be used to do a bootstrap? Can you comment on such things?
There are all kinds of things you can analyze. Yeah, there's modular bootstrap, which works very well in 1+1 dimensions, but in 2 dimensions we don't, or in 3 dimensions, let's say. What kind of modularity would you like to consider? Because I can look at the 3D CFT on a torus, then I have modular invariance, but I have a spectrum of states, a Hilbert space now, which is defined on a 2 torus, and that doesn't correspond to local operators. My state operator correspondence only works when my Hilbert space is defined in radio quantization, so I have a little sphere that I can shrink to a point. It's a 2 torus, I cannot shrink it to a point, and things break down. So you might be able to say something there. People have explored that very little. There's also finite temperature, where you just take, in 3 dimensions, S2 cross S1. People have analyzed that a little bit. You can add a boundary. We did some work on that. So consider a d-dimensional CFT on a half space and analyze the boundary crossing equations and so on. So there are all kinds of crossing equations like that you can analyze.
Now let's think the speaker again.